Hello everyone, this is Dr. N.G. Praveena, working as Associate Professor, the Department of ECE at R.M.K. College of Engineering and Technology. In this video lecture, I am going to discuss about the concepts of delta modulation. The outline of this presentation is Introduction, Features and Principle of Delta Modulation transmitter block diagram and its working, followed by the mathematical expressions, delta modulation receiver block diagram and its working, drawbacks of delta modulation, signal to noise ratio of delta modulation, and finally concluded with the applications. When we modulate a digital signal with any modulation technique, the primary requirement is implementation of the system. So, the implementation should be as simple as possible. Delta modulation satisfies this by oversampling the message signal. Hence, the transmission bandwidth is effectively utilized in delta modulation. Thereby, it is considered as a dual of differential pulse code modulation. Here we are going to discuss about the features of delta modulation. Some features are highlighted here. The quantization design of delta modulation is simple. The input sequence is higher than the Nyquist rate. Modulator and demodulator of delta modulation design is very simple. The step size which is used for approximation of x of t and u of t is very small. The bit rate can be decided by the user. Here we are going to discuss about the principle of delta modulation. The delta modulation transmits only one bit per sample. It is said to be a 1 bit or 2 level version of DPCM. Here the input signal x of t is approximated with the staircase signal u of t, and then it is quantized into only two levels, either plus delta or minus delta. When the approximated signal u of t is less than x of t, it means the difference is positive, then u of t can be increased by plus delta and thereby 1 is transmitted. If the approximated signal u of t is greater than the signal x of t, then u of t can be decreased by minus delta, then 0 is transmitted. This is the concept that is applied for delta modulation. It shows the waveform of delta modulation when x of t is greater than u of t, when x of t is less than u of t. You are going to consider only these two cases. When x of t is greater than u of t, 1 is transmitted. When x of t is less than u of t, 0 is transmitted. This slide shows the delta modulation transmitter block diagram. The transmitter block diagram consists of an accumulator block, a comparator block, a quantizer block and an encoder block. The comparator compares the sampled value x of NTS and the last approximated signal x cap of NTS, and the error signal it generates, that is your E of NTS. So, I can write down E of NTS as x of NTS minus x cap of NTS. This is applied to a 1 bit quantizer. The 1 bit quantizer output is taken as EQ of NTS. So, I can write down EQ of NTS is equal to, it is del SGN of E of NTS. So either it will transmit plus delta or minus delta. Here when x of NTS is greater than x cap of NTS, then plus delta is considered. When x of NTS is less than x cap of NTS, it is taken as minus delta. Plus delta is nothing but 1, whereas minus delta is nothing but 0. The summer in the accumulator block adds this 1 bit quantizer output, that is plus or minus delta, that is nothing but the output of EQ of NTS to the previous sample approximation. Thereby U of NTS can be written as U of N minus 1 TS plus del SGN of E of NTS. Right? Can you able to understand? Now this here initially the accumulator is taken as considered as 0, so this is taken as 0. So I can rewrite from this U of NTS is equal to del S Gn of E of NTS. So depending upon the sign of E of NTS, the quantizer produces either plus delta or minus delta. Here the delta modulation receiver block diagram as shown. It consists of an accumulator and a low pass filter. The input has been represented as B of NTS since we are transmitting only bits. The output of the accumulator is taken as U of NTS. It is delayed with a time period of TS. So I can write this as U of NTS minus TS. And the output of the low pass filter is taken as X of T. The accumulator reconstructs the staircase approximated signal U of T from the incoming sequences of positive and negative pulses, that is either plus delta or minus delta, either 1 or 0. If the input is binary 1, the accumulator adds plus delta to the previous output. If the input is binary 0, then the accumulator subtracts minus delta from the previous output. The low pass filter has a cutoff frequency which is equal to the highest frequency in X of T. Thereby it smoothens the staircase signal. The drawbacks of delta modulation as discussed here. There are two drawbacks we have in delta modulation. One is said to be a slope overload distortion called a startup error. The other one is granular noise. What is slope overload distortion? When X of T is greater than U of T. When the input signal X of T is so high that the staircase signal cannot approximate it, then this error will occur. The next error is granular noise, also known as hunting. Here X of T is less than U of T. It means the step size delta becomes too large. Step size becomes too large. This error should be decreased when the slope of the signal X of T is very low. Now we are going to derive the signal to noise ratio of the delta modulation. Assume we have a sinusoidal signal of frequency F0 and amplitude A0 is represented here. So X of T is equal to A0 sin 2 pi F0 T, where A0 is the peak amplitude of the signal and F0 is the signal frequency. Now we are going to find out what is the maximum slope of the signal. So I am going to write down the slope of the signal. Maximum of d of X of T divided by dt is equal to, differentiate it, So you'll be getting like this 2 pi f naught a naught when you differentiate it. The maximum slope of the delta modulator is taken as del by, this is a maximum slope of delta modulator has been taken as del by Ts. When the slope overload distortion occurs, it occurs when the slope of the signal, when the slope of x of t is greater than the slope of delta modulator. If this condition prevails, then slope overload distortion occurs. So what is slope of x of t? Substitute here. It is 2 pi f naught a naught should be greater than del by Ts. From this, what is a naught? A naught is greater than del divided by 2 pi f naught Ts. Now we are going to arrive a condition for the slope overload distortion. It will not occur when a naught is less than or equal to del divided by 2 pi f naught Ts. Now I am going to derive the signal power based on this. I am going to find out what is the signal power. I am going to derive the signal power. I know the amplitude of the signal is A naught. So the maximum amplitude for A naught I should get to avoid slope overload distortion is del is equal to 2 pi f naught Ts. Now I am finding the normalized power. So P is equal to, I can write down A naught divided by root 2 the whole square. So when I substitute A naught here, after squaring I will get del square divided by 8 pi square f naught square Ts square. So this is your signal power. Similarly, I am going to calculate what is the noise power. I am going to calculate what is the noise power. How to calculate noise power? Assume Q is a quantization error which is represented by a variable, random variable Q. Represented by a random variable Q. When you draw the distribution curve for this, I am writing the distribution curve here. It follows fq of q with the amplitude 1 by delta over a limit minus delta by 2 to plus delta by 2. Find out what is the mean of this quantization error. With the help of mean, I can find out the variance. So I am finding out the variance here. Find out the variance of this noise. So I can write here the variance of the noise as sigma q square is equal to. What is the limit I can write down? It is minus delta by 2 minus infinity to plus infinity q square fq of q into dq. So here the limit is minus del by 2 to plus del by 2 q square into 1 by del into dq. Here take 1 by del common, integrate it and substitute the limit, you get del cube by 12. So from this I can write this as del square by 12. So now substitute the value of del as 2 del. So I can write down sigma q square is equal to del square by 3. So this is your variance of the noise. Now the noise has been confined to a bandwidth of plus or minus W. So we are writing the average output noise power. I am writing the average output noise power as, say, I am drawing the spectrum of the noise. I am drawing the spectrum of the noise here. It is S of f. Okay. Then this is your plus Fs over a period minus Fs. It is confined to this region with the limit minus W to plus W only in this region. So by applying this, I can write down as it is W Ts into del square by 3. This is your noise power. Finally, I am going to find out what is the signal to noise ratio. It is average output signal power to that of average output noise power, a del square divided by 8 pi square f naught square Ts square into W Ts into del square by 3. By cancelling the terms, I finally end up with the expression 3 divided by 8 pi square f naught square W Ts cube. The maximum output of SNR output of delta modulation is inversely proportional to the sampling rate cuboid under the assumption of no slope overload distortion. What are the applications of delta modulation? Here it is used for the voice transmission system such as radio and telephone communications, and we can apply this in the medical diagnosis for ECG waveform, for database reduction and real time signal processing. Thank you all.